Hello, in this video we're going to talk about the normal distribution. This is topic 1.10 from the AP Stats course and exam description. All right, so there's three objectives for this topic, although we're not going to discuss all of them in this video. I'm going to break it up into separate videos. Let's see, the first objective says to compare data distribution to the normal distribution model, determine proportions of percentiles from a normal distribution, and compare measures of relative position in data sets. Okay. So we're going to focus on just the first two objectives, which is to look at the normal model and then figure out proportions and percentiles. Okay. So let's first talk about a parameter. Okay. So in a previous video, I showed you this diagram, and we talked about a statistic, right? So a statistic is a number that's derived from a sample. Now, a parameter is the opposite of that. It's a number that is derived from a population. Okay. So in this figure, we have the entire state of Massachusetts. We can think of that as the population, and three separate samples that have been drawn from that population. Okay. And there's numbers describing each group. Okay. So this number here, the 78 millimeters of mercury, is describing everybody in the state of Massachusetts, right? So everybody in the population. So 78 is a parameter, okay? These other numbers of 75, 67, and 71.3 are describing each of these individual samples, okay? So those are statistics, okay? But they're not parameters. All right, so you'll see in a minute why we need to introduce this term of a parameter. So there's a lot of data out there that kind of follow this particular shape. They're mound-shaped and more or less symmetrical. And so for data with this shape, we can use a normal distribution, okay, to model it. In other words, we could imagine that this data came from a population that's described by this normal curve, okay, sometimes referred to as the bell curve. Okay. So the histogram is representing sample data, but this bell curve, this normal curve, is a model for population data. All right, so because the normal curve is going to represent a population, we're going to use parameters to describe it or define it. So normal distributions are defined by just two parameters, the mean, and we use the Greek letter mu, and the standard deviation, in which we use the Greek letter sigma. Okay. So whenever we're talking about parameters, we often use Greek letters to represent them. And when it comes to samples, we use Roman letters for samples and statistics, sorry. Okay, so for this model, we could say that the mean, or the center, is 52, and the standard deviation, the spread, is about 13.5. Okay, I don't have any units because I didn't put any context with this graph. All right, so something very cool about normal distributions is that they all follow what's called the empirical rule, right? So every normal distribution will have 68% of its data falling within plus or minus 1 standard deviation of the mean. And then 95% of the data will fall between plus or minus 2 standard deviations of the mean. And 99.7% of the data will fall between plus or minus 3 standard deviations of the mean. Okay. So some people call this the empirical rule. Other people just call it the 68, 95, 99.7 rule, because it just helps them remember, right, the percentages as we widen the interval around the mean. All right, so I'm going to go ahead and work out some problems with you in which we would use the empirical rule. I'm switching to my document camera. There it is. All right. So many studies on automobile safety suggest that when automobile drivers must make emergency stops, the stopping distances follow an approximately normal distribution. Suppose that for one model of car traveling at 62 miles per hour, under typical conditions of dry pavement, The mean stopping distance is mu equals 155 feet with a standard deviation of sigma equals 3 feet. All right, so what's important in that introduction? First of all, they're telling us that we can model this with a normal distribution, and they provide the mean and they provide the standard deviation. Okay, so let's go ahead and just sketch that normal model. So what I like to do, zoom out a little bit. Whenever I'm drawing a normal model, I like to use the centimeter side of a ruler. And then I like to, let's see, we're gonna have 1, 2, 3, 4, 5, 6, 7. Okay, I like to put 7 marks. To extend that a little bit. Sorry, that didn't come out good. Okay. So the mark in the middle is going to be for the mean. And then going out a mark, either left or right, is 1 standard deviation away, then 2 standard deviations away, and then 3 standard deviations away. All right. So drawing normal curves might be a challenge at first. What I like to do is I like to start with a point to represent the peak of the curve. And then I go about halfway down from my next 2 points, and then about halfway down again, and then about halfway down again. Okay, and then just sort of connect the points. All right, so the mean is 155 feet, so we can place that value in the center of our number line, okay, below the peak. And then the standard deviation is 3 feet, which means each of these increments will be of 3. So this will be 158, 161, 164, and then going the other way, we're just subtracting 3 now, so 152, 149, and 146. Okay, so not only should we scale our number line, but we should also label it, right? What's the variable that these numbers represent? And it's stopping distance. And then does this have units? And it does, the units are feet. Okay, so we would expect based on this model, okay, that your average or typical car will take about 155 feet to stop. The worst cars are going to take, up to 164 feet to stop. And the best cars are going to take about 146 feet to stop. Okay, a lower number is better in terms of stopping distance. All right, so now that we've drawn the model, let's answer some questions about the stopping distances. Part A, about what % of cars of this model would take more than 158 feet to make an emergency stop? Okay. So more than 158 feet is describing a region in this model. Okay, so I'm going to go ahead and highlight that using pink since I underlined the phrase in pink. Okay, so more than 158 feet. So there's 158 feet. Okay, so that region there represents the proportion of cars that would take more than 158 feet. All right, so how can I figure out the size of this area? Okay, when all I know now is the empirical rule, right? 68, 95, 99.7. Okay. Well, I could say, because of the empirical rule, that 68% of cars will have stopping distances between 152 and 158. And I know if I look at all the cars would be 100%. So now that I've labeled the center region as 68, well, how much percentage do I have left over, right? So I've got 100% minus 68%, which leaves me with 32%, okay? But that 32% would be split evenly into both tails. Remember, this is a symmetric distribution, so that's how I know it would be split evenly. Okay. So now if I just take 32% and divide it by 2, that will give me the region here that I shaded. Right? So 32% divided by 2 would be 16%. Okay, so we could safely say 16% of cars would take more than 158 feet to stop. Okay, so we've got 68% in the center here, 16% in the right tail. So we could go ahead and say that there's 16% in the left tail as well. Okay, so just so that every region here is labeled with a percentage. Okay, so 16, 68, and 16. Right, part B. A car of this model that takes 158 feet to make an emergency stop would be at about what percentile of the distribution? Justify your answer. Okay. So the word percentile refers to the percentage of observations equal to or less than a value. Let's write that somewhere. Percent of observations equal to or less than a particular value. Okay, but in this case, that particular value is 158 feet. Okay, so we're trying to figure out what percent of cars would have a stopping distance that's 158 feet or less. And so we can, because of the phrase less than, right, we're going to shade everything to the left of 158 feet. So find 158 on the number line, and then we're just going to shade all of this. All right, so this yellow region here is made up of the 68 and the 16. So we just need to add those two, and that tells us the total percent of cars that would have stopping distances less than 158. Okay, so 68% plus 16% would be 60, 70, 84%. Okay. So a car whose stopping distance is 158 would be at the 84th percentile. Right, since 84% of cars would stop in less than that distance.